Okay, good morning, everyone. Going to get you to do me a favor and open up your unit handout to page 22. So put away the assignment that's due, I think, Monday. I initially said your flying pig lab was due today, but I said yesterday that it was due Monday as well. So please put all of that away. Yesterday was kind of a work day where we got more practice with satellite motion. And you were given that assignment, which is due Monday, and some of you were still working on that circular motion lab dealing with the flying pig. In the meantime, we're going to move on now to the next part of this unit, which deals with energy. This whole unit is called Circular Motion and Energy. We've done the circular motion part, and now we're going to be looking at the energy part. What we're looking at today is going back to Science 10 and defining some things that you worked with last year in Science 10 in a more sophisticated manner. It's the same with, on Monday of next week, we're going to be dealing with kinetic energy and potential energy, which you learn about probably in Science 9 as well as Science 10. But the level of sophistication of the work we do with these ideas is going to continue to grow. Very similar to in the kinematics unit when we spent a whole week talking about uniform motion, which is basically speed equals distance over time. Things got more complicated than they did in junior high or grade 10. Today what we're looking at doing is defining work done to an object and energy of an object, and explaining very clearly why these things are scalars. And I put that in the objectives here to try to impress that upon you right now. Somehow, for some reason, students want to take the concept of energy and elevate it, for some reason, to the status of being a vector. Energy is not a vector. Energy has no direction. And neither does work. Even though we're going to be calculating work using vectors, the result is going to be a scalar. And then, as I just said, we're going to be calculating work. We have a couple of definitions to begin with, and the definitions, although I've told you we want to bring things up to a higher level of sophistication here, although we want to ramp things up here, the definitions are childishly simple. They really are. Energy is the ability to do work. That's it in a nutshell, as my grandpa would say. Boiled down to its essence, energy is the ability to do work. So if you have energy, that means you have the capacity to do work. Well, what's work? This is where things become a little unsatisfying in our definitions, because work is a transfer of energy. And the reason why this set of definitions is kind of unsatisfying is because they define each other in terms of each other. Right? I mean, what's energy? The ability to do work. Okay, well, what does work mean? Oh, it's a transfer of energy. It becomes almost cloudy, like a dog chasing their tail. But let me tell you right out of the gate that energy and work are both measured in joules. There are other units of energy and work. We could use calories. We could use, I think it's called an erg, E-R-G. There are other units of work and there are other units of energy. Or better yet, there's other units of work and energy. But the standard unit is joules. So whenever we do any calculations that involve standard units like meters or seconds or kilograms, we get joules. So what does this mean? Okay, so I wake up in the morning and I have breakfast. And inside of the breakfast I eat, there's chemicals. And then my body takes those chemicals and through a process of chemical reactions changes them to other molecules, but those chemical reactions are what we would call exothermic, which means they take energy out of those chemicals. And that energy is stored, well, it's stored in my muscle tissue. I can use that energy to do things. Do what? Walk around, talk, load stuff into my vehicle. And all those things that I do is work. So if I want to do work, I need energy to do work. So what happens is that when I eat, the energy inside of me goes like this. It doesn't happen like that. It's not like I'm being filled with energy that way. But this is just an analogy that the energy in my system increases and increases and increases. And then I stop eating. And immediately after, and even while I'm eating, the energy is starting to drop again because my heart is moving. That's work. That work of moving my heart and even breathing requires energy, because energy is the ability to do work. So what happens is, when I do that work, I transfer the energy out of my energy store into something else. And by the way, it eventually all becomes heat. Okay. So to maybe make this analogy more specific, if I have a certain amount of energy in my body and I want to take a baseball and throw the baseball, I have to do work to the baseball, whatever that means. Well, what it means in this context is I have to transfer energy from me to the baseball. So let's say that I give the baseball 100 joules of kinetic energy, which is a type of energy we'll review on Monday. What that means is if the baseball has 100 joules of energy afterwards, I have transferred 100 joules of energy to the baseball, which means I've done 100 joules of work, which means the energy has dropped by 100 joules inside of me. And this is where we get an important concept with work that we're not really going to deal with today, but it's never too early to introduce this, that if work is a transfer of energy, then the amount of work done is how much energy is transferred. If I tell you that in lifting a box from the floor of my garage to the shop bench required 500 joules of work, and I said, how much energy did the box get? It got 500 joules of energy. If I say to you that when my car is in motion, it has 5 million joules of energy, and then I said, how much work did I have to do to get the car to move that fast? The answer is I had to do 5 million joules of work. It's a subtle difference, but the work done is the amount of energy you give an object. We could take this step one step further. If I take that baseball and I throw it to give it 100 joules of energy, then I have lost 100 joules of energy in me, right? So that my transfer of energy is 100 joules, which is the work. If that baseball is flying towards you and you're sitting in the stands, I throw an errant pitch at a ball game, and you're too busy trying to order a hot dog, and it hits you in the head, what that 100 joule energy baseball has is the ability to do 100 joules of work. So when it hits you in the head, it can transfer that 100 joules to your head. By the way, during every collision, you're going to lose some energy to heat, which is an important idea in Physics 30. Does anybody have any questions about energy or work in this limited set of definitions? Okay. There are different ways that we could calculate the amount of work done. One of them I've already alluded to. It's this. You can always find the number of joules of work done by just finding the final energy of the system and the initial energy of the system and just subtracting them. That would be the work that was done. And again, I know that I'm being overly repetitive here, but if there is in a system, there is 40 joules of energy, Then you look away for a second, and when you look back, there's 140 joules. So the system goes from having 40 joules to 140 joules. And I said to you, using language from physics in high school, what just happened? The best answer is somebody did 100 joules of work to the system, because they've transferred 100 joules to the system. If, on the other hand, we go from 140 to 40, somebody has done a negative amount of work to the system. Now, before we go on, can things be negative if they're vectors? No. Negative 9.81 meters per second squared means 9.81 meters per second squared downwards. Okay? Can things be negative if they're scalars? Temperature, right? Negative 20 degrees Celsius it was this morning, maybe. That doesn't mean it was 20 degrees Celsius south. It just means on some scale it was negative. Can work be negative? Yes, work can be negative. If work is negative, so I know I'm throwing a lot at you here, but if work is negative, then that means the initial energy is more than the final energy. The system has lost energy. If the work is positive, then the initial energy is less than the final energy. And by the way, I regret writing these in the order that I wrote them in. I should have written the EIs and EFs backwards, because change in work is final minus initial. So final minus initial gives you a positive value. You have more at the end. That's another thing we're going to have to grapple with. But let's make a note here. Not only are these measured in joules, they are also both scalars. And I don't know if this is going to come up again in the lesson. It might, but I thought I would mention it here because I blindly walked into going from 140 to 40, which is a negative amount of work, and I wanted to address that. So although there are different ways to calculate work, one being final energy minus initial energy, one way that works to calculate work is to talk about the force that's applied and the distance that the object moves because of that force. And it turns out that the amount of work done to an object is the product of those two things. If you multiply force times displacement, you get work. But you have to use the component of the force that's in the same direction as the displacement. So a classic example, and I'm going to jump ahead here. Don't worry about anything else. Just look at this situation here. If I have this box of dynamite, trinitrotoluene, TNT, and I pull it at that angle with a force of 85 newtons, and the thing slides across the floor 25 meters, to find the work, I'm not going to multiply those two forces, because that force is not in the same direction as the displacement. Now, I'm going to stick with this. If I did ask you to find the work, and let's actually do this example. Let's flip over to this example. It's at the bottom of page 23, I think. Yeah? So I've told you that the work done is the force times the displacement, as long as this is in, well, what I've actually said is the component of the force in the direction of the displacement. Right, that's what I've told you. We can go back and you could read it, but I've told you that one way to calculate work done is to multiply the force by the displacement, but the force has to be in the same direction as the displacement, or it has to be the component. Well, you're all smart. You can find the component of the force that's in the direction of that 25-meter displacement. It's a trigonometry problem. The hypotenuse, vectorally speaking, I don't know if that's a word or not, but in terms of vectors, the hypotenuse of this little vector diagram is the 85 newtons, and the angle is 20 degrees. So if we want to find this component of the force that is in the same direction, which is an x direction, we would use, I guess, cosine of that 20 degrees equals that component of the force that's in the horizontal direction over the hypotenuse, which is 85 newtons. So we can take 85 multiplied by cosine of 20, making sure we're in degree mode. I just say that because I go back and forth to radian mode in another of my classes, and I get 79.87 newtons. So then we can take the force times the displacement. It's really that simple. It's not a difficult formula. So the work done would be equal to 79.87 newtons multiplied by 25 meters. I want to say 2,000, or very close to 2,000. $19.97. And this was one of the rare cases, everybody, where I put the units in because I just want to tell you, and I don't want to get it sidelined today into a discussion of why, until maybe near the end of the class I might, about why this is the case. But when you multiply newtons by meters, you get joules. Okay? So when I say to you this formula is not a complicated formula, it really isn't. The downside is that's not how it appears on your formula sheet. And I'm going to tell you, not, I don't know, some teachers might disagree with me here, but I'm going to tell you not, do I have it here? No. To worry about how the formula appears on your formula sheet. I mean, I have to talk about it because otherwise you'll see it and you'll wonder what's going on. This is under dynamics because, it's not. It's under momentum and energy because it has to do with energy. There it is. Work equals FD cos theta. So work is force times displacement. But the force has to be in the same direction as the displacement, which means the force actually has to be the horizontal component if it's moving horizontally. If you look at what we did when we solved this problem, we took the force of 85 newtons and multiplied by the cosine of the angle. That's your F cos theta. The issue I have with this formula, and now I can show it to you in your notes, if we go back to the first page of this lesson, this is the formula in your notes that's the same as the formula on your formula sheet. The issue I have is I think it overly complicates things, but you need to remember theta is a specific angle. It's the angle between the force and the displacement. So if you were given an angle that was, say, between the force and the vertical, that wouldn't work in this formula. I would prefer, although in Physics 30 I go back to this formula the way it is for a reason, but I would prefer that you say to yourself, this is how we used to write it. Work equals FD as long as the force that you're using is parallel to the displacement, in the same direction or opposite. This brings up some interesting ideas here, everybody, which is that I'm told by some students that as punishment for not doing their homework, their parents do this. They have to stand like this. For a while. And it's already my arms are, I'm not the fittest person in the world, but I'm okay. But it's starting to get irritating. I'm not doing any work to these books. Because the books, even though I'm applying a force upward on them, they are not moving upwards or downward. They're not moving in the same direction. I am losing energy, so I'm doing work to something, and I'm doing work to my heart muscles, which are beating faster. I'm doing work to the tissue in my muscles, which are continually contracting and expanding in order to supply this force. I could go on, but I don't feel like it, so I'll put those down. It's quite challenging. So, according to these students, that's why they do homework, because if they don't do their homework and their parents find out, they have to stand there holding their textbooks for a while. So, no work is being done in that case. No work is being done right now. No work is being done right now. Am I applying a force to this 3-hole punch? Yes. Is the 3-hole punch experiencing a displacement? Yes. Are they in the same direction? No. I'm applying a force upwards, and it's moving perpendicular to that. If I apply a force upwards and it moves perpendicular, what's the angle between the two? What's this angle? 90 degrees. What's cosine of 90 degrees? Check it out. What's cosine of 90 degrees? Nothing. You learn about in Math 30 why that's the case. Actually, in Math 20, we talk about that. So, mathematically, that makes sense. Physically, it makes sense because if you look at this force, this is my arm that's representing the force. What is the amount of this force that's in that direction? Nothing. There's no horizontal component to this force, so the force in the direction of the displacement is nothing. There's all kinds of subtleties with this. The other thing I really have to stress is that this is the applied force. It's no longer the net force, it's the applied force. I don't care whether there's friction or whether there's gravity. Whatever the force is that I apply is the force you use in determining the work that I do. If you want to know the work done, well, in the spring I like to garden, and I got a little dog. She's a little terrier, and I put her to work. I got a wagon that I fill with dirt, and I harness her up to it, and she pulls the dirt around for me. I don't do that. But if I wanted to know how many joules of work Scout, that's her name, Scout does, then I have to use the force that Scout applies and the displacement of the wagon that Scout pulls. You don't use the force that I apply, which is almost nothing because I'm just sitting in my chair enjoying a cold drink while my dog is doing all the work. You do the force that she applies. Okay? It's always the applied force. We use standard units of newtons for force and meters for displacement, and we get joules. And again, perhaps later today I will explain why we get joules out of that. I think I will, but I just don't want to do it right now. So some notes. Even though force and displacement are both vectors, the product of them is not a vector, it's a scalar. And that's reflected, by the way, here, when you look at the formula on your formula sheet, that's reflected by the absolute value signs. That's a clue that even though those are vectors, when we multiply them together to get the work, we're not including the directions. And I take issue with that a little bit, because if the force is in the opposite direction, I think you should put a negative in for the force to get a negative amount of work. It's reflected in my version of that formula because I don't even have vector symbols above those. So really I'm saying it's the magnitude of the parallel component of the force, the parallel component of the applied force, times the magnitude of the displacement. So that's the first note. The second note, again, one more time, the force in the formula is the applied force. If you're trying to determine the work done by a monkey that's pulling a wagon, then you have to use the force applied by the monkey. If you want to know the work done by friction, then you would use the force of friction. If you want to know the work done by gravity, you would use the force of gravity. And we do talk about work done by gravity. We'll do that tomorrow. Third note, I've already talked about, even though work is a scalar, it can be positive or negative. To put it another way, if the work is negative, that means delta E is negative, and what that means is EF minus EI. I don't know if you remember this. I don't know whether you should or not. I hope you do. Delta is always final minus initial. So this has to be negative. How are you going to get a negative number if you take the final energy and subtract the initial energy? If you had more energy to begin with, which means you've lost energy. So if the energy, show this to you in one more way, if you're talking about the energy in a system, going from here and dropping and going to there, you're talking about a work being negative because the energy is dropped. Has anybody taken Chem 30? That's why an exothermic reaction has a negative delta H. In chemistry, you use delta H instead of delta E. That's why. It's the exact same idea. And if you had, on the other hand, you have the following, where the energy goes from some value in the system and it increases, then you've added energy, and that's the definition of a positive amount of work. So even though work is a scalar, work can be negative. In physics 30, we'll go even further and say, you know what, we can use negatives for energy as well, but that's a little more confusing to explain at this level. Okay. So, question, what happens to the formula if the angle between the force and the displacement is 0? Let's see. So I have an object. Let's draw a diagram. I have an object. Let's go with the traditional box that everything appears to be in physics in high school. And we're saying that you apply a force in this direction. And the object moves in that direction. This is what it means to say the angle between the two is 0. Or, no, I don't want to do that. This is what it means to say that the angle between them is 0. So what happens to this formula? What happens to work equals FD cos theta? Can you forgive me for not putting all the vector symbols and absolute value signs? We're just worried about amounts here. Well, this would be FD cos 0 degrees. What is the cosine of 0 degrees? Check it out. It's 1. which means that it's work equals force times displacement. And this, 9 times out of 10, this is the formula we'll use to calculate work in terms of force and displacement. Because a lot of the time, they're just in the same direction to begin with. Number 2, what happens if the angle between them is 90 degrees? So again, we're going to take an object, we're going to apply a force. Maybe the force is up. This is an applied force. And as a result of that applied force, it moves not as a result of that. The object happens to move to the right. So the angle here is 90 degrees. What happens to the formula is work equals FD cosine 90. But cosine of 90 is 0. So what happens is the work is negative. I have a third question here I'm going to add under the questions section. What if I want to try to draw a connection here between physics and math. What if it's 180 degrees? What does that mean? It means that we have an object, and again we'll go with the traditional box. We have an object that's resting on a surface. Just wait for my computer to catch up. Not hovering, but resting on a surface. And it moves this way. Well, there's a force this way, and it moves in the opposite direction. First of all, how can that happen? Alex?
Is it like with the pushing thing and it pushes back?
No, it's not. It's not Newton's third law. Well, if I'm driving a car to the left and then I hit my brakes, do I continue to travel to the left? I mean, I'm driving this way, and I hit my brakes, which applies a backward force. Does my car immediately start moving backwards? No. It starts slowing down, losing energy, by the way. So you're talking here about an angle between these two of 180 degrees. So this means the work done is FD cos 180. Now, unless you've taken Math 20, you're not used to thinking of cosine or sine or tangent of angles unless they're between 0 and 90. But go ahead and calculate the cosine of 180 degrees. It's -1. There's a reason for that. And again, if you've taken Math 20 already, you will understand that reason. But what that means is that we end up with work equals FD multiplied by -1 or negative FD. Now, FD is a positive thing because F and D are both just the magnitudes of those quantities. So this is just demonstrating that if F times D is 100 joules, the work done will be -100 joules, which means you're removing energy from the object. Okay, Wile E. Coyote. You're familiar with Wile E. Coyote? Genius. Attaches a rope to a 670 kilogram piano and lifts it straight up at a constant speed of 22 centimeters per second to a height of 10.2 meters, because what could possibly go wrong, right? How much work is done by Mr. Coyote? Well, work equals the applied force times the displacement in the direction of the applied force. Here's our piano. Here's the floor or the ground. This is a rope. I don't know what kind of pulley system he has, but he's going to be pulling that piano up to a height of 10.2 meters. Well, it doesn't matter. Okay, so he's pulling it up to a certain height somehow. The height is 10.2 meters. What will the force that he applies be? No. Not greater than the force of gravity. There's something here, yes and no. But what we have to do is say it's the force of gravity. Who can tell me why in this question that the applied force is in fact the force of gravity? Right, it's moving at a constant speed. We're not going to actually use that 22 centimeters per second or whatever it is in any of our calculations. So, Alex, yes, you are right. In order to get it moving, you have to exceed gravity to begin with. But we're talking about during that change in position, which is displacement, we're talking about a constant velocity. So as this thing is moving up, let me just add one more thing here. As this thing is moving up, to a higher and higher position, that's weird, doesn't matter. As it's moving up to a higher and higher position, we go back to the previous unit and we say that since it's moving at a constant speed, the force due to gravity is equal in magnitude to the applied force. Now, there might be problems later on where I give you an acceleration and I say how much work is done. Well, then you might have to use some dynamics and some vector diagrams to determine the applied force. So what do we get here? Let's just keep building this. The force due to gravity is mg. So the work done in this case is mgd. We just take the mass of the piano times 9.81 newtons per kilogram times 10.2 meters. (670 kilograms times 9.81 newtons per meter multiplied by 10.2 meters. Sometimes I like in this course to talk about the units. We know, pardon me, this is newtons per kilogram. We know that when you multiply mass times g, since the gravitational field of the Earth is newtons per kilogram, those kilograms cancel, and that's why you get a force of gravity in newtons. But we also know, based on what I've told you today, that newtons times meters gives you joules, so we're getting joules here. (670 times 9.81 times 10.2 is 67,042 joules. Does anybody else get that number? Except I didn't write it down correctly. 67,042 joules. What does this mean? It means that as well as being an idiot, Wile E. Coyote now has lost 67,042 joules of energy in his body in the effort to get more energy by catching the Roadrunner and eating the Roadrunner, which never happens. Right? That's the brilliance of that cartoon. What else does it mean? It means that when Wile E. Coyote, in his exhausted state, ties the rope, he maybe forgets to tie it properly, and then he climbs down and he stands there looking around, and he looks up and the piano comes crashing down on him. It means that the piano is going to end up doing 67,040 joules of work to Wile E. Coyote, but it's not going to put that energy back into stored energy in his body. It's going to put it into breaking things, flattening things. Well, we've already done this one. That didn't work, so he finds because apparently he has money to buy dynamite from the Acme company, but he can't, phone for takeout or something. He thinks, well, let's try to blow up the Roadrunner. We've already done this, right? The point of this lesson, or the lesson of this example, is that you have to use the force that's in the same direction as the motion. All right, let's take a look at number 3. What's he up to now? How much work is required to push this 10-kilogram box of nails to the top of the ramp if the ramp is greased so there's no friction? First of all, if it's greased, you couldn't walk along the ramp, right? So maybe it's being pushed up by pushing with a pole. What we need to do here is find out what force is needed, what applied force is needed to move the box to the top of the ramp. Well, the applied force needed, if we're going to move it at a constant speed, and I really ought to have put in this example at a constant speed. Okay. Otherwise, there's no right answer to the question. You could just keep using a bigger and bigger force. If it's at a constant speed, which means no acceleration, what is this force that I have to apply to overcome? Because if there's no friction, shouldn't I just be able to just push it really easily? What do I have to overcome here, Jay? Well, I do have to overcome gravity, but it's not the force of gravity. It is a force, the parallel component of gravity. So I have to overcome the parallel component of gravity, which means that if I'm moving at a constant speed, the applied force is the parallel component to gravity. Okay. So let's find that first. The parallel component of gravity is the force due to gravity times sine of theta. You don't have to memorize that. It would give it to you on exams. Okay. So this will be Fg parallel equals m, which is 10 kilograms. 10 kilograms times 9.81 newtons per kilogram times sine of 25 degrees. About 41.459 newtons. Are you getting the same number? Okay. Now, that's a force, everybody, along the ramp, which means you need to also determine the displacement along the ramp, because the force and displacement have to be in the same direction. Well, that's a trigonometry problem that's based on distances. Let's see. This is opposite the 25. This is the hypotenuse. So we're going to use sine of theta is equal to, well, opposite over hypotenuse. we get sine of 25 degrees equals 4 over the hypotenuse. So we can find the hypotenuse, and then we can find the work done by going force times displacement. H here will be 4 divided by sine of 25 degrees. So I get 9.464. Work will be the product of those two, right? This force times this displacement. I've stored that force in my calculator as A times my answer gives me this number. Now I want to show something to you. The explanation as to why what I'm going to show you will work will be given to you tomorrow. The full explanation. The answer, if we carry all of our decimals, is 392.4 joules. What if instead Wile E. Coyote took that box I'm guessing Wile E. Coyote wants the box to be at the top of the ramp. That's the goal. Because at the top of the ramp, the box has this much energy, doesn't it? That's the work he did, so at the top, it has that much energy. The box has that much energy at the top, regardless of how it gets there. So, what if I said to you, how much energy is required to just lift that box 4 meters? Then it's like the piano question, isn't it? Which would be the force of gravity, which would be 10 kilograms times 9.81 times 4. The point I want to make, and there's another way to explain why that works, and I'll do that tomorrow, not tomorrow, but you know what I mean, Monday, is that since the box gains an amount of energy equal to the work done, the final state of the box tells you how much energy the box has, so it doesn't matter how you get there. I can push it up a real low-level ramp that climbs slowly up to 4 meters. I can lift it straight up. To get it to that point requires that amount of work. A couple more. Describe and explain what happens to the already weak and delusional Wile E. Coyote after performing all of these tasks in the previous examples. He's tired. He's weary. He's lacking energy because all of this work he did is transferring energy out of his body. So Wile E. Coyote has lost a lot. We could calculate. I'm assuming in question 3 that it was him pushing the box to the top of the ramp. We could calculate it. What do we have? 392. 1997, we're at about 2,400. I'm doing some liberal rounding here. 2,400. About 71,000 joules, approximately. Give you a rough idea here. It may seem like a lot of energy, but in terms of, say, a Big Mac, we're used to things like calories. 540 calories. I mean, a Big Mac is not the healthiest thing in the world. If it's your thing, it's delicious, but I don't think you'd want to eat 3 or 4 of them every day. I don't think that would be good for your body. 540 calories is over 2 million joules. So this is not a huge amount of energy. Okay. I also point out how much energy this is because can you imagine actually doing these things, like the 670 kilogram piano? You're not burning a lot of energy. You really, and those of you that have workout regimens, you know that you need a lot of exercise to burn calories. It's not like, you eat a 300 calorie chocolate bar and expect to go for a walk and burn that off. It doesn't work that way. We could do a ratio here, and I'm getting a little off topic, but again, as a class, I think we have things to learn that are not always in the curriculum. You could take 2,250,000 divided by 540. So there's about 4,000 joules in a calorie. That's it. Like 1 calorie is that many joules. 1 calorie. So how many joules did we say he did? 70,000? He's burned 17 calories. Now, he's already very weak, right? So every calorie, he's not trying to shed the calories, he's trying to get calories in. Or he's just psychotic and just wants that Roadrunner. He goes home and has a fridge full of food, and this is just a game to him. But I'm assuming he's hunting for survival. All right. Any questions with that final example related to 1, 2, and 3? All right, Rocky. I ran out of things for Roadrunner and Wile E. Coyote to do. Rocky and Bullwinkle, you ever watch them? Old stuff. Like old. It was old when I was a kid. Rocky's driving a 1,250 kilogram car at 95 kilometers per hour when a moose, Bullwinkle, runs out into the road. Well, you don't want to hit the moose for a number of reasons. So he locks the brakes. Rocky, he or she, locks the brakes. When the vehicle comes to a stop, the length of the skid mark is 88 meters. How much work is done to the car? Wait a minute. How much work is done to the car? So here's the moose. I'm not going to make any kind of lame attempt to draw Bullwinkle or a moose. There's the moose. Here is the car with Rocky in it. There's the headlight. There's Rocky. I'm not going to draw it so you can make out his features or her features because I don't know. I'm not that good of an artist. Rocky sees Bullwinkle. Rocky slams on the brakes. Rocky started here. And Rocky finished there. The length of the skid mark on the road is 88 meters. So while the car was stopping, while the car was skidding, what is the force doing the work to the car? What is the force doing the work to the car? It's not gravity. It's not the engine. While Rocky enters the skid, he or she might as well just turn the ignition off because the wheels are locked. What's the force doing the work? Friction. So what's happening is there's a displacement to the right of the car. This is the displacement. And there is a force backwards not causing the displacement, but causing the change in the energy of the car. And this is the force due to friction in this case. The applied force in this case is the force of friction. But that's not going to work, is it? We could, if we knew the coefficient of friction, we could find the force of friction, couldn't we? Is there any other way we can find the force of friction? There is. Would you agree the applied force is the force of friction? The applied force is the force of friction. Are there any other forces acting on the car while it's moving? Alex, what's one other force? Gravity. And by the way, I'm just going to temporarily move this out of the way because this is not a force, right? So we also have a force due to gravity. Why can we ignore the force of gravity? Because there's a normal force. So what, in addition to the applied force being the force of friction, what else is the force of friction? The what? The net force. Which means we can calculate it using MA. So this force of friction is the net force, which is MA. I bet you never thought that those kinematics formulas would rise up from the grave and rear their ugly head in our direction again, but they have. We've got to use the information in this question to find out the acceleration. VI is known. VF is known. It's 0. D is 88. So we can find the acceleration. What do we have to remember about the 95 kilometers per hour, though? Jay? Right. We want meters per second, so we're going to divide that 95 by 3.6. So 26.38 repeating. I'm just leaving the units out here. How do we find the acceleration? I know it's been a while, but VF squared equals VI squared plus 2AD. So we're going to have 0 equals 26 squared plus 2 times A times 88. I just knew I wouldn't have enough room to write 26.38 repeating, so I just wrote 26. So I have to square this number. Mathematically, I have to subtract it to the other side where it becomes negative. Then I have to divide by 2, and I have to divide by 88, which means the acceleration is negative 3.96 meters per second squared. Which means the net force is the mass times the acceleration. That's not right. The mass times the acceleration, that's the net force. Which is the force of friction, which is the applied force. So now I can go work equals applied force times distance. So I'm going to multiply that applied force by the displacement of 88. And that's my answer. What's the negative mean? It means that the work was done to remove energy from the car. It means the car lost 435,233 joules of energy. Just put it into standard scientific notation, gives me negative 4.4 times 10 to the 5. A lot going on in this lesson. Again, we've graduated a long way from saying, oh, here's a formula, use the formula. You got to figure out how to use the formula. I want to point something out to you, though. And I'm just going to do this so that we can refer to it on Monday. Can somebody tell me, and you might not remember, all of you, but I'm sure somebody does, what is the name of the type of energy that the car has when it's moving? Declan? It's kinetic energy. Do you happen to remember the formula for kinetic energy? It is. It's 1/2 mv squared. So kinetic energy is 1/2 mv squared. Okay. Does the car have kinetic energy at the end when it's stopped? No. So the final energy is 0 minus the initial energy. Well, let's calculate 1/2 mv squared of the car to begin with. Let's see. 0.5, I just go 0.5. I don't go 1 divided by 2. Times the mass, I guess we got to do this first. 95 divided by 3.6, right? So now I'm going to go 0.5 times the mass of 1250 times that speed squared. It's 435,233.1444. It's exactly the same number, isn't it? And when I take 0 minus that 4.4 times 10 to the 5, I get the work done. Because work is force times displacement, but work is also change in energy. So we could have just found the change in energy of the car and not worried about that whole force of friction and all that other stuff. No kinematics. And what we're going to discover is when you approach many of the problems in the right way in this course from here on in and in Physics 30, you can weasel and maneuver your way around the kinematics and not have to use it. Anyway, got some questions to practice. I'm not going to do number 6 today. We're going to do it on Monday. I don't think you want to do trig. There are some attached problems. You will only be able to do... You will only be able to do 1 to 7. There might be some more on the next page that you can do, but what I would like you doing, and you have about 15 minutes left in class today, do 1 to 7 for sure. And then we'll finish this off. There's one more thing we want to talk about relating to graphs. We'll finish that off on Monday.